Now the next property of convolution is distributive. So what does this mean? So it means that if you have an input x of t that needs to be fed to two different systems, let's call them h1 of t, another system with this h2 of t. So you feed the same input to two different systems, okay, and then you add them. If this is your system, essentially it's modeling this scenario, right? X of t is fed to two different systems and then you are adding them together. You can replace this entire setup with just one system such that the impulse responses of the individual LTI systems are added together. So when you have parallel connections, you can add them together. So the earlier property, commutativity and associativity, helped us to tell what happens when you have series connections, right? So when you have series connections, you can just put these systems in any order. Now distributivity talks about what happens when you have parallel connections with a addition or a subtraction at the end. So if there is an addition or a subtraction at the end with parallel connections, what you can do is you can club everything together into one system where the impulse response is now the addition or subtraction of the individual impulse responses. Now, why is this true? It directly follows from the linearity of the convolution property. So this is, if you remember, this exactly looks like the superposition property, right? We said convolution is true for linear systems, which means there is linearity already inbuilt, and that directly follows from the superposition property of linearity. Now, if you think of this property, a very simple example where you can see that this becomes useful is our initial audio equalizer example. So we had an audio equalizer. Basically, we had multiple systems there. So if you remember, we had a low range system, a mid range system. These systems are basically nothing but filters, right? So we had a low range frequency filter, a mid range frequency filter, a high range frequency filters, right? So we had to give the same input to multiple filters and have different gains for different filters. So the low range would increase the bass of the audio and the high range would increase the volume of the high frequencies such as percussion instruments and so on. So what we are doing in that particular case is exactly corresponding to this scenario. So this is an analytical expression of the case which is very similar to the audio equalizer, where we give the same input to multiple filters which have different gains and then finally add them together. So what this property tells us, you actually don't have to construct multiple filters. You can have just one filter such that the impulse response of this one filter is corresponding to the sum of the impulse response of these individual high range, low range, mid range filters. So this is very interesting because earlier we thought we need multiple filters to do one audio equalization. But what this property tells you is that as long as the system that you are constructing is an LTI system, the filters that you are constructing is an LTI filter, you can always replace that with just one block, one system which can do this operation of filtering out multiple frequency bands with different gains. This actually helps us in practice to constrain the number of devices that we need, discrete components that you need. You can reduce that by using this property. So this is very useful in that manner.